Before we introduce the next axioms, we're going to talk about formulas. A formula is something with symbols that you replace with sets and then get a statement that is either true or false. So one example of a formula is x equals x. You can replace the x's with, for example, the empty set and get the statement empty set equals empty set, which is a true statement. Another example of a formula is x equals y. Here you can replace the x with the empty set and the y with the empty set and get the same true statement, but you can also replace the x with the empty set and the y with the set containing the empty set and get a statement that is false. So using these formulas, or the idea of formulas in general, we come to the next axiom, which is the axiom of comprehension. And it says that for any formula phi with free variables among x and w1 through wn for all z for all w1 through wn, there exists y such that for all x, x is in y is equivalent to x is in z and phi is true. So when we say free variables, we just mean letters that can be replaced with symbols. So in the previous example, both the x's and the y were free variables. And so what this axiom is saying is that you can take any set z and you can specify what these free variables w1 through wn are with anything, and then you're guaranteed that there exists a set y which satisfies this following clause, which is that if x is in y, then that means that x is in z and phi is true. And if x is not in y, then that means that either x is not in z or phi is not true. So it's basically taking a set z and taking out of it only the elements which satisfy this formula that you can really have a lot of freedom in deciding what it is. And so this axiom is the one that's going to allow us to get rid of those ellipses that we had earlier. If you remember, before we had a set A and B, and by the pairing axiom, we had a set that contained A and B and maybe some other stuff. And so if we want to get rid of this other stuff, well, we would use the comprehension axiom with the formula x equals A or x equals B. And so now, if x is not equal to A and x is not equal to B, then this formula phi is going to be false, and so the element x in this case is not going to appear in the new set that we create using this formula. The same goes with the union axiom, and here it's pretty simple to actually come up with the formula that we need to get rid of the ellipses in that case. The formula is simply copied from the definition, and it's x is in y and y is in F. And so, using this formula, we get rid of all the other things that were in our set, the things that were not in sets that were in our family that we were unioning over. And so we get a definition of a union that makes sense to us, which is that the union over a bunch of sets just takes the elements in all the sets and lumps them together. So for our next axiom, we're going to want to turn formulas into functions. So we want a function that maps elements from some set, A, to other sets, which can be any sets. So we're going to use V to talk about the universe of all sets. Now it's important to remember that this is not a set. It's the thing that you get when you put all the sets together, and the whole point of this axiomatic system was that this is not going to be considered a set. But we can still have functions that take elements from A and map them to elements from the universe of all sets. So this is still okay. And so our formula, to turn our formula into a function, we're going to want it to have a specific condition, which is that for every x in A, there exists a unique y satisfying V. And so this exclamation point means that there exists something, but it's unique. So it always comes after the backwards E, there exists symbol, and it means that not only does this thing exist, but there's only one of them. So because of this, you take your x in A, and then you find the y that satisfies phi for x, and that is going to be your image by this function that you're defining with this formula. So one example of a formula that we can turn into a function is x equals y. And so here, we'll say that A is going to be equal to the set containing A and B, little a and b. And so using this formula on this set, well, we get the image of this set is going to be, well, for A, what's the unique y such that A equals y? Well, it's going to be y equals to A. So we get A again. And the same goes for B. We end up with the same sets. It's not very interesting. Another more interesting example might be the formula, the set containing x is equal to y. Here, when we use the formula with the same set, we take A and we replace x with A, and so we get the set containing A is equal to y. And what is the unique y that satisfies the set containing A equals y? Well, that is going to be the set containing A. So we end up with the set containing A being an element of our new set, and similarly the set containing B in our new set. And so, as I'm sure you can anticipate by now, our next axiom is going to say that we can take sets and take their images by these formula functions that we've made, and those are going to be sets as well. And so the way to write this out precisely is that for all A, for all W1 through Wn, if for all x in A, there exists a unique y satisfying phi. This is our clause that says that phi can be turned into a function that we just discussed. This implies that there exists a big Y such that for all x in A, there exists little y in Y satisfying phi. And so this is the part that actually constructs the set that we want to make. And so the set is, we're calling it big Y, and for every x in A, we have a little y and big Y that satisfies our formula. And so, similar to the union and pairing axioms, we're saying that there exists a y in big Y that satisfies these things for each one in A, but we never say anything about extra elements being in this set. So once again, we end up with these ellipses that we will want to get rid of, and we can get rid of them using the comprehension axiom in exactly the same way.